Le haut-parleur et le micro.
Yeah, it's fine.
Okay, shall we start? I hope that people online are already connected. If there is any problem with the Meet platform, just please type a message so that we are aware of any problem. And so I'm now glad to introduce Marcus Stumtre from the University of South Australia, who is going to give us a keynote speech, Ontology Lifecycle Management, Digital Twins in the Digital Ecosystems. Marcus is director of the Industrial AI Research Center at the University of South Australia, and is also program leader for the digital technologies and interoperability in the future energy and export cross-cutting system. Is part of the ISO technical committee, especially for the domain of oil and gas interoperability. He has co-authored several papers which span across multiple engineering and computer science areas like Industry 4.0, self-aware systems, autonomous decision making, complex event processing, software engineering, software system debugging, and so on and so forth. So I think that we'll really listen to a very interesting talk. And I'm now glad to give you to leave you the stage.
Thank you.
Thank you, Marcus.
Is the mic working? Good. All right, thank you. So I added the subtitle. I hope this is enough buzzwords, but we'll come to why they're in there. So I was asked to talk a bit about my experiences with this industry, and partly to keep the talk within the allotted time, I'm going to try and avoid talking about specific ontology design. I'm not going to prefer particular ontologies, also I'm going to mention some. And the talk also does not explicitly prefer any particular ontology languages, also particular ones are going to be mentioned in particular projects, right? Horses for courses. So I want to start, as several people today have done, with talking about the digital transformation that is happening right now, and then how that leads to digital ecosystems. And then we'll talk about how ontologies can fit into those ecosystems. These are just going to be small case studies, which you can look up in other papers. And then at the end, I'll turn towards looking at ontologies from a software engineering point of view and see how they fit into the overall software engineering development ecosystem, and close with some challenges. So the digital transformation, which is all around us, right, is the change of the industrial environment over the last 20 or 25 years by the universal application of digital technology. There's many labels under which it comes: Industry 4.0, Industrial Internet of Things, digital twins, and there's many domains that are affected. If you mention Industry 4.0, then typically people think about discrete manufacturing, but really the origin of, or the first successful applications of that sort of technology were in the aviation space. The one thing that's usually mentioned is the Boeing 777 about 30 years ago, and before that NASA with the moon landings, who had essentially digital and physical twins of their moon rockets. Right? Where that sort of digital twin for individual products is now heavily used is in the vehicle space, right? So companies like Daimler now have something which they call the software-defined vehicle project. But you also find it in areas that are not usually associated with that sort of technology, for example, in what's called precision agriculture, where people are looking at studying the social behavior of individual cows on the pasture to find out if they're sick or healthy. And a particular area that we have been working frequently is what we call the process industry. So there's oil and gas or chemical industry. And this is different from manufacturing, that there's not a discrete product, you've got an ongoing process. And so the key aspect is not so much the product life cycle. The typical key aspect is the plant life cycle, which makes things interesting in a number of ways. So on the basis of this digital transformation, happen digital twins. Now, this is a very short, the first part of the definition given by the Digital Twin Consortium for Digital Twin, virtual representation of real-world entities and processes, synchronized at particular frequencies and fidelities. And that's about the part that is non-controversial. I come from a one-week workshop on digital twins, and at the end, people had a hard time converging even on a definition. Right? Because the question is, does the digital twin report back? Does the digital twin learn? Does the digital twin evolve? If it doesn't do any of these things, is it a digital twin and so on? Right? So there's a lot of variation. Just as there's a lot of potential use cases for digital twins, right? So the one idea is to use them for simulation, but then you extend that into monitoring, prediction, optimization, and all kinds of virtual engagement operations and training. Now, in the public image, the last one is so frequent that we created this slide to explain to people what we mean when we talk about a digital twin. And the digital twin is not just the 3D visualization, right? Which also is the first thing that you normally get when you do digital design, because you get your 3D CAD model. And then you say, oh, wow, it's a digital twin. No, the point of the digital twin is that you can do more with it, but that's not necessarily part of the direct 3D visualization. Right? So you've got simulation, you've got analytics, you need communication so that you can get the data out of the cyber physical system into the digital twin. You have some sort of information models, and intentionally fairly deep down are potentially ontologies, right? So this fits into what we had this morning in the Siemens stuff, where the ontologies were the orange layer on top of everything else. This turns it around, but basically it means if you've got everything in place, the ontologies may help you do certain things more effectively. Going back to that process domain that I talked about, this is the life cycle of very large scale asset, industrial plant, process plant, which starts out with some sort of abstract design, manufacture of the individual components. The process engineers that design the plant run simulations to work out what the parameters should be. Then there's detailed engineering design, procurement of the parts, and construction. Right? And then this is handed over to the operator and begins to operate and maintain, which is a totally different phase. In reality, of course, this is the really long part of the life cycle. Construction may take a few years, but a typical chemical plant can last for 40 or 50. The key part is that each of these boxes in the life cycle typically is using different software tools and possibly by different vendors operated by different contractor companies. And that is where typically interoperability question comes in. Each of these boundaries is an interoperability boundary where you need data translated or somehow communicated across. It's made more complex by the fact that in addition to the individual contractors, there may be overarching interests. There may be a particular software vendor that says we have a unified solution, or there may be platform integrators, large consulting companies that basically live on building the ultimate integrated software solution for the owner-operator. The usual outcome of these approaches is that you get a bespoke solution that does very well what you want when it is new, but you're then locked into the same vendor for about 40 or 50 years. And basically you have to go back every time something massive changes in the plant, you have to ask them to re-implement it. You can't switch, right? This is what's known as vendor locking. So the owner operators in principle have interest in obtaining interoperable solutions so they can have a actual marketplace of vendors and switch between systems later on. So where's the digital twin? The digital twin basically is in the communication across these stages, because if you have full digitalization, you can take the experience from your operations, you can learn from it, you can control the plant better, you can optimize operations by comparing it to history, and you can also update your engineering models, your 3D plans and so on, as changes get made to the plan, as maintenance happens. So because that can potentially involve all of the different systems that support this particular life cycle, that's why we talk about digital ecosystems, by which we mean essentially digital software ecosystems. Now, traditionally, when you hear the term digital ecosystems, this was usually phrased in terms of a single vendor, the Oracle ecosystem, the SAP ecosystem. Right? What we see here is a hardware ecosystem, it's a Lego ecosystem, right? You need to fit the blocks or you can't work with it. Interesting enough, the Lego model is used to show a real world interoperable ecosystem, namely transport supply chains, right? Where effective marking and container dimensioning mean that extremely high flexibility is provided worldwide. So what we're talking about is more the second kind, which is a functional ecosystem. We're looking at different systems coexisting in the same space, because ultimately nobody in that ecosystem usually is big enough to swallow everybody else. So they need to get on the digital. Right? And again, that can happen in most of the various domains where you get digital transformation. And in particular, it refers back to this particular example. So then along come people and say, we need interoperability, what about standards? Right? And this is a situation that we all know. If you're in a situation where there are N standards, somebody comes and says, we're going to do the universal standard, replaces all of them. At the end, you have N+1 standards. Right? None of that is necessarily bad, but you need to accommodate it, right? And so even the standards do not change the fact that ultimately you're going to be in an ecosystem where multiple things happen in parallel. Right? So this is a very old slide, it's about 15 years old, used by permission from Chevron. It shows their picture at the time of the standards that look at a chemical plant or oil and gas plant life cycle, right? You see the different stages from left to right, as we had before: engineering, procurement, construction, operations, and capability, which means maintenance. And the vertical dimension shows how close you are to the control system. And right at the top is enterprise management, purchasing, and business stuff. Right? So that's 2006. What this looks like now, it's about like that. But there's a host of digital standards produced by different organizations that all describe different aspects of the plan that are particularly relevant. On the left-hand side, you've got more industrial-oriented standards organizations. On the right-hand side, you have international standardization, like various ISO groups, right? Which have, for example, things like ISO 8000, which is data quality, 55000, which is maintenance, 62 IEC 62264, which is communication buses and so on. Right? And all these standards exist in parallel, sometimes compatible, sometimes not. Right? We're engaged in something which is called the Open Industry Interoperability Ecosystem exercise, which looking at how these standards can be federated. Right? So the idea is to build something that's called a supply neutral ecosystem, where public standards are sufficiently well specified that you can actually plug in and execute different implementations, which is by no means guaranteed for all the standards on the previous slide. this is the architecture behind it. I'm not going to explain it in detail, but what it basically shows is the communication paths, again, between the different systems that operate in this plant space. We've got control systems, which actually run the plant. And then they have some sort of communication platform, which is called a bus, that communicates with the operation systems, and then the enterprise systems. That's standardized by ISO. So this is the diagram that's in the ISO standard, because ISO doesn't like colors. And what I'm showing here is a different view of the same architecture, which is done by cooperation between multiple standards organizations. So in this case, it's the view from ISA. And what they've done is they've looked and plugged in a particular standard here in the control systems, which is OPAS, the Open Process Framework, as a control system for process plants. If you were looking at a manufacturing system, you might have, for example, OPC UA in it. So we've got this ecosystem. Now, where do the ontologies fit in, right? And the answer is you've got to cover the different interoperability challenges that you have in this ecosystem. You need to do mappings between the various models and the information models, let's call it that, that are in there. The physical system, the software systems, the processes that drive the software systems, potentially the communication model, because in there you've got information about what data format is it, what's the schema like, what's the actual payload, what is the message that you're trying to communicate. And ideally, you want the ability to have meta modeling that describes the interaction, and then an ontology that gives you the terminology. I'll try to make this as short as possible, but basically there's a number of examples that we ran that looked at the ontology space in that environment. This is the first project that we did. That's actually now about 10 years ago, and it looked at automotive design. So we have what's called multidimensional optimization. Right? Basically, a car design cycle, regarded abstractly, is like this chain here at the top, where you have a design cycle where the designers go through simulations to work out how well a particular part works. Right? This is what's called a crash box, which runs through some numeric simulation. So each of these individual cycles does multiple simulations to work out what the part should look like. Right? And then they come together and they try to fit all the parts together into the vehicle. And this takes a lot of computing power in today. But the problem is, after 2 years, the data are useless because nobody remembers where they came from. And if you want to extend this, you need to know how to run it and what data to run it on. So basically what we were asked to build was an ontology-driven description of the process that ran the simulations and that kept track of the data that went into this. So what you're seeing here is basically the deployment diagram that looks at the different solvers that build the geometry, that build a mesh for analysis, and that do dynamic analysis. And they use various configuration parameters to put out outcomes of the behavior of a particular part. Yeah, I already talked about it. One thing that helped was this was a development organization with high maturity, so they were basically a high-performance computing center, and they were willing to work with whatever languages would be used. Right? So in that case, we put together a solution that said, okay, we have multiple ontologies. We've got ontologies that describe the tasks that you're trying to execute. You've got ontologies that describe the artifacts you're trying to build. And we used dedicated languages for the job, because the point there was not so much interoperability with other companies, but within the workflow. So we used a formalized version of UML. For the meta modeling, we used OWL for particular domain abstractions, because there were ontologies that we brought in from third parties, and the task specifications were formalized in PSL. Second case study is basically what we did in the oil and gas space, process plant lifecycle. What you're seeing here is a block diagram of a refinery, and the yellow box at the bottom is a fractionation tower, which we saw earlier. And I think Francesco's presentation, that takes particular components out of the raw material, the raw oil or gas. So in this case, it's what's called a debutanizer. It takes butane out of the original raw crude oil. What we're seeing here is the beginning of the life cycle of the debutanizer. Literally, this is a photo of the diagram that was drawn on the whiteboard by 3 process engineers to say, okay, this is what this thing is going to look like, and we're starting to fill in the instrumentation and some performance parameters. And when we've got that, then we go to the design systems and produce a process and instrumentation diagram, P&ID, to fill it out and start putting in all the information in mechanical form. You do that in editing systems coming from CAD vendors. And the key part is that, of course, all these are subtly different. But in the end, what comes out of this, if it's built, so in that case, we were doing a pilot study, so it didn't lead to an actual physical thing, but that's what the debutanizer tower looks like in an actual refinery. So what do you want to do with this? You want to carry this data across the life cycle. You want to do handover, which means give it over to the operator. And you want to make sure that the data are consistent. You want to automatically move them between systems that use different data standards and possibly different ontologies. Even if you have ontologies, different vendors or different parts of the functionality may be covered by different domain ontologies. And you want automatic configuring of parameters. So what this gives you is that you move from a data ecosystem to what is essentially an ontology ecosystem, where you have to negotiate between different ontologies that fit the data together. What makes it more interesting is that the partner organizations are very varying in their maturity. Some of them don't want to look at anything but spreadsheets, basically, right? Which is what engineers feel comfortable with, and they say, just give me a CSV file, right? Refinery might make up 300,000 spreadsheets, but that's fine. So you need to be able to communicate in the format that the engineers want, and you have to be able to map the data back if they make changes to it. So the first use case that we did this with was about 8 years ago. That was handover. And we've since been modeling different use cases in that space that look at different things that the company, the owning company, and the procurement, the contractors can do to the plant, right? And they have to do things like various kinds of maintenance triggering, notifications, all kinds of replacement parts and maintenance actions, right? And we're filling these out in detail. That you can see again the brown color on the left and the green color on the right is the 2 stages. EPC on the left-hand side and operations and maintenance on the right-hand side. This is one of the demos that we did, showing the automated translation of the P&IDs, some of which in various ontology-based standards based on ISO 15926. Also, this was for part 14, so that's not included. And it automatically transformed the data into the CCOM standard, which is one of the standards that's used on the operations and maintenance side. And what it did basically, so here you have the CAD diagram using Bentley tools of that debutanizer tower that you saw earlier. Here you have the same thing drawn with Aviva. Here you've got the same thing drawn with Intergraph. And if you use the transformation, then you end up with the same plan on the other side, where IBM system at the time, integrated information graph, was used to actually parameterize and execute the control systems. There was an ontology in this. Well, the ontology aspect was in describing the mappings between the data models on the left-hand side and the right-hand side, which were at different levels of expressivity. The data model on the left-hand side included things like ISO 15926 part 2, which is a story on its own for those who know it. The data model on the right-hand side was Mimosa, but other variations could have been used. event. This was based on a ontology aligned with Deutsche for various reasons. What we're doing now is continuing to build these use cases that you saw in the earlier diagram by refining them from very simple, what we call stories, down to a level where they can be formally specified and expressed in formal languages to enable automated execution and in particular validation. So you can run test data and you can formally check if a particular vendor produces outcomes that are consistent with your specification. The third study is an extension of this, which is based on our voice paper from last year, where we're looking at the question of what if we don't want to shift systems between the different stages in the life cycle, because the data that is handled varies considerably. You start out with high-level design data, then you go to detailed design data in CAD systems, and eventually you go to the records of the physical assets. Right? Each of these phases has different constraints, but you want to relate them to each other. So basically what we did at the time was we created you could call it a meta-ontology approach that enabled within the same ontology to have a reference to the information object that describes a particular physical part, and to evaluate the descriptions to work out that whether particular, for example, measurement values or environment parameters that are applied to a particular device are actually satisfied at a particular time. So this requires particular modalities for the constraints. You need to be able to describe what is the environment envelope where the device operates correctly. And if it is in that envelope, what kind of performance measures does it have to provide? Again, because it was an extension of the earlier work that was based on Deutsche, using standard concepts, descriptions, and relations. And what we then did is we introduced a fine-grained definition of constraints that allowed decomposition and evaluation of these constraints. It required a particular ability to reference device's own description. And we used a particular variation that we had done in the earlier project of artifact types. So we distinguish artifact kinds, which are functional definition, and we have artifact species, which look at functional aspects. The key part is that the artifact types are defined in a way so that the classification of the device is maintained, even if not all of the functionality is guaranteed, right? So a pump that is broken down is still classified as a pump, even though it can no longer pump, right? Which usually leads to all kinds of contortions as one tries to maintain consistency in one's fact state. The approach also supports constraints across what we call multiple levels of classification. So it's from the pump to the type of the pump, but also from the type of the pump to particular pump models or particular kinds of pumps, such as rotating equipment and so on. And we worked this out in a way so that it can be implemented in multiple ways, which is what the ongoing work is about. So this is an approach that references the primitives of the ontology. It must be able to reference a contextual object, so the device that we're actually looking at. And it needs to be able to refer to the usual ontological qualities, quality regions, and all kinds of logical conditions. So this would then be an example, a relatively abstract one in this case, of a pump, which is connected to an impeller that actually does the propulsion of the material through the pump. And then we have the ability to specify individual properties for an instance, and we can propagate this across the actual instantiation relationships to work out which conditions of the operation situation are satisfying, which ones are not. We did this using different constraint languages, again, depending on, to some degree, what environment the industry partner wants to work in. Theoretically, the most elegant ways to define this as first order or even higher order logic, but you can implement it as if you use meta programming by redefining the constraint rules. And from the software engineering perspective, if you want to do what's known as model-driven engineering approach, you would use the object constraint language, which is part of the UML standard, and which can also have subsets that have formally defined semantics. We've got some projects that are currently going on. These are funded by new research center, Future Energy Exports Cooperative Research Center, funded by the Australian federal government for the next 10 years, looking at liquid natural gas and hydrogen production efficiency to keep them efficient, competitive on the world markets. And what we're doing in these projects is basically looking at the later stages of the life cycle, in particular operations and maintenance, to look at how particular analytics software providers could tie into this ecosystem in interoperable way, so that you specify what kind of requirements and what kind of parameters and what kind of behaviors your analytics should cover. And then any provider whose software satisfies those formal constraints can be bought by the owner operator and can operate in that plan. This is something that's particularly interesting to small and medium enterprises who can basically demonstrate their capability to be used in particular parts of a plant formally, right? And that way get a leg in relative to large vendors. And again, the description of this is at the semantic level. Now, so to close up by looking at things from a software engineering point of view. One of the issues that we're dealing with is from the perspective of the industry partners all the time is, from their perspective, ontologies are software artifacts, which means they cost money, which is usually the key aspect of industry partners, that they want to save money. They may also be interested in quality and operations, but that's because better maintenance, for example, reduces the number of failures, which cost in more than ineffective operation. Right? So ultimately, it comes down to cost. So from that perspective, an ontology is a software development artifact that needs to be maintained over time. And the question is how much effort that costs, and the question is how much effort it takes to be integrated into the existing code base. That may also be the case for vendors who say, we've got an integrated automation solution. We don't need that ontology-based aspect that we have. I'm not going to talk about quality, because pretty much all we normally talk about when we are talking about ontology modeling is about quality, finding the best ontology for the job under particular circumstances. But the other pressure that happens in the area is that developers generally have a desire for simplicity, right? And so whenever complex standards are introduced in a particular area, there is the risk that over time, the software engineering community that needs to implement and run these systems drifts off or substitutes this with some simpler version, right? So classic examples are SOAP versus REST, where complex protocols and data exchanges were replaced with something simple. You can't do everything, but developers find it simple. XML versus JSON. Again, XML does more, but is unwieldy to handle in many cases, so developers came up with JSON. Now, what then happens is that over time, people chafe under the restricted ability of the simpler approach, and they say, can't we get some of that back? That way you get things like JSON schema, right? But rarely is the replacement then necessarily as good as the original. So what's happened on the semantic side is that we have RDF, but RDF functionality to a certain degree has been mirrored by property graphs, all kinds of graph databases, some of which are openly available, some of which, like Google Graphs, are internally used. But again, there's the perception that some of this is easier to use, and therefore it gains market share. The second aspect is how much effort is required to maintain an ontology. There's a guy from the University of Bundeswehr in Munich who did some work while he was at Dairy in 2006 on what he called possible ontologies. How big can ontologies get if they rely on free maintenance? And track this by looking at essentially web-based updates. And what he realized is that there is a trade-off between the expressiveness, the complexity, the size, and the number of users, right? Because the more complex it is, the bigger it is, the more effort it takes to update it. So if you don't put money in, certainly with the tools at the time, the effort to maintain this and keep it operational and updated exceeds the possibility, and then it falls out of use. Flip side of this is define ontologies as standards, in which case they're taken care of by standards committees. But having complex models defined as standards can be risky. So this is the STEP experience, where the standards experience was defined so solidly that they cannot update it except in 5-yearly cycles, which makes it ineffective. This was then replaced by ISO 15926 Part 2, which had its own problems, trying to do too much in one go, and is now being replaced within ISO 15926 by 2 different substandards, Part 14, which is, as far as I can know, quite good and quite effective. But there's also Part 12, which uses slightly different modeling. So we have the N+1 standards problem. Now, other software domains find the same problem. So there's a very nice survey paper of BIM, Building Information Management. So this has similar aspects to the same examples we've seen. There's a well-defined interoperable base of data models, which is the industrial foundation classes for about 15 years or so. It has an automatically creatable semantic extension, IFCL. And it's used for the development of digital twins in what they call n-dimensional BIM. So 3-dimensional is CAD diagrams. 4-dimensional, confusingly enough, it's cost measures. And there's 5-dimensional, I think, sustainability and so on. What this study found was, yes, all of that exists, but it's still too weak. The digital twin functionality typically needs manually inputted additional resources, which makes it expensive and slow and error-prone. And instead of the full-fledged standards, companies tend to link only the 3D part of their models with the other software packages that they already have. So this comes back down to the code base of the infrastructure that is already in the company. Even if you have an ontology that theoretically covers everything, the company may still decide, no, we want this part over here, and then you need to execute it and interoperate with it. And all kinds of information that are hidden in the semantic extension were found to be not comprehensive enough for actual use. One particular aspect where we have approached is that basic interaction in BIM is still document-oriented, so you dump the plans for the building, and it's not transaction-oriented, where you query particular parts of your knowledge graph based on the properties in the ontology, and then you send just a fragment across to get the information for a particular transaction. So what challenges does it leave us? And obviously, this is an extremely subjective view, but one thing that is probably interesting is how much of the tools and techniques improved since HEP's days. How big can the ontologies be that depend on free updating? And can they, to what degree, can they keep up with the rate of change once the ontology is defined? The second one is if you assume that you're dealing with an ontology ecosystem, you need, or even if you use ontologies just to maintain your data ecosystem, how expressive are ontology languages for mappings? The ontology alignment workshop, which has been going on again for over a decade, look at probabilistic mappings, which are better used for search applications than for transactional business data. Right? If you're mapping part numbers, you need to know that the replacement part number is right. The Deepwater Horizon accident happened in part because of the operating crew did not know they had the right parts or not. Second, if you have different formalisms, let's call that, whether at ontology level or data level, that have different degrees of coverage. I'm not talking formal expressiveness, just what is actually covered. Transformations will, in one direction, result in loss of information. So you can either accept that and accept that you're not going to have the return direction, or you need to work out some way in which you keep a repository of what that lost information is linked to so that you can map it back, which significantly complicates your architecture. Last two bits is the question of how to improve representation techniques for industrial settings. The first of these is closed word assumption. Right? We keep getting told the semantic web formalisms, look at open word assumption because you don't know what's out on the web. But if you operate in an industrial or business environment, most of what you do is actually closed word assumption. Right? You do not buy a part that's not in a catalog somewhere. If it's not, then that doesn't mean there's an unknown part that exists. It likely means that somebody mistyped the number. Right? And the second aspect is, and also that came up in one of the presentations this morning. How do you constrain views that are supposed to be readable by non-ontologist users to the domain terminology that they are familiar with? Right? Any ontology will have auxiliary classes or concepts that will not likely be directly understandable to the engineers that we try to communicate to. And so you can't simply give them a dump, you have to hide that information and express the discrepancy in either possibly code formulas or natural language descriptions. But theoretically, you would need an easy way to separate out these labels, and you can't simply just say, okay, I've got the unique name assumption, and so everything I have is globally visible to everybody who looks at this ontology. Unless, of course, you separate the end user completely from the ontology, and then the work falls onto the ontologist to show what they communicate to the user. So, summary, digital transformation is a great time for ontologists, right? It leads to the creation of very large digital ecosystems, and that gives phenomenal opportunities to ontology modelers, but it also means that just as with other levels of modeling, you're not going to have the universal ontology. You're going to have an ontology ecosystem, and actually that triggers a whole host of exciting new research questions from my perspective. Thank you.
Thank you very much, Marcus. So is there any comment or question from the audience? Yeah. Sorry.
So Marcus, and by the way, Marcus and I have known each other for a while now. You talked about the importance of tooling and sort of presenting to the user terminology that they're comfortable dealing with. As you kind of look over the last couple of decades, what do you see that encourages you, and what do you see that discourages you about sort of the state and the direction of tooling?
The encouraging thing, I think that sort of functionality is eminently doable. But there is a tendency to just use what is already available, right? It's not all a question of a consistency check. Putting your ontology in the reason and saying, okay, it all works out. The question is, you need essentially, to some degree, ergonomic analysis, or at least the ability to distinguish within the system what are the bits that are actually terminology that an end user, if you want a non-specialist end user, would be familiar with. Right? And to some degree, that could be as simple as working out, okay, here's certain base concepts, right, that are going to be expressed with a simpler name, because I can't pack the exact specification in that I would like to have and show it to the user and they will understand it. So there's ways of doing it, right, but somebody needs to do it.
I mean, thank you for an extremely wide-ranging talk. I just want to pick up one sort of tiny aspect, which is of growing interest, which is the simulation data management. You talked about, the keeping track of the information flows through a simulation process, and you have all these results files, and you might not know where they come from, for what they're valid, without the appropriate metadata. What I want to flag up is that there is a NAFEMS group, which is the International Association for Engineering Analysis, and it's working jointly with INCOSI and has a team on simulation metadata. And I think a fraction of this presentation would be extremely useful for that community. And are you involved in any other work taking that particular area forward?
Was that a question?
Basically, is there anything more? Is there more work in that area going on? Are you involved in it all?
Not at the moment. I mean, if that group is working, excellent. But to some degree, the work that we find evolves from the, how should I say, the shallow to the deep end of the iceberg. Right? You build the infrastructure and then you worry about the deeper problems. At the moment, for some of the problems that we're describing, we're still building the infrastructure.
Is there any other question? Yeah. You said ontology is basically software. So if it's software, what is the commercial software market you see? I mean, so in a sense that we see all of these companies doing knowledge graphs and all that sort of stuff, but actually on the ontology itself, there's still, I mean, there are a few, but very little. So if ontology is software, why is that?
That's a good question, right? There's two possible answers, right? One is that there is not widespread awareness of the benefits that you can get, right? And we saw some very high percentages mentioned in this morning's keynote, right? That awareness is there. That's great, right? But I know that quantifying benefits in this sort of activity is typically extremely difficult because the industry partners themselves don't know. Right? So that's one aspect. I was thinking of a second one. Give me a second. It's gone. Sorry.
Thank you. There's a question from the web. So Sana Debek, if I'm pronouncing this correctly, asked, what do you think about the BIM usage to build digital twin? Is it a necessary solution?
I think the BIM community, which is ahead of some others, right, has found it extremely useful. I mean, BIM has been mandated in the UK, right? And so there you have data and they can do more. And I think they've been very happy with it. The classic digital twin application that I mentioned is obviously aviation, right? Which is unimaginable these days without digital twins. That's how planes are built. The interesting question, and this is one that nobody has been able to answer to me, is that also why planes are so expensive to build? Because we've now gone to an ecosystem where basically the two largest plane makers in the world can only afford to build a plane a new plane every 15 to 20 years. And then, as in the case of the A380, you get interoperability issues and you have years of delay and billions of costs. Right? So that's pure speculation, right? But it could be effective.
Okay, thank you. Okay, maybe the last question.
Okay, I like very much the contrasting between simplicity and quality that you made, especially for ontology, because I think like most of the ontology work, especially formal ontologies, it's clearly on the quality side. So do we have a perspective of how we could achieve a good balance between these two aspects? Is that something that it's just a matter of awareness and people have just to do it, or is it intrinsically difficult?
To some degree, I think it is intrinsically difficult because that's the problem of doing work on declarative code. Right? It's a non-trivial matter. You still need, like with any other software, you need execution, validation, testing. The other part is, to some degree, we're perhaps not exploring the space as much as we could. We've had standards for 15 years and they're ingrained. We're getting tool after tool on new standards. But and this goes back to the industrial perspective, when I work with an industry partner, I adapt the tool to the problem normally. I don't try to adapt the problem to the tool, because it doesn't work.
Okay, thank you. Maybe we can continue the discussion during the coffee break. Let's thank Marcus.
Thank you very much, Marcus. Now we move to the two paper presentation. So let me